Welcome to our first super learning seminar of the semester. Today we have Sergio Cristancho telling us about reverse Khovanskii-Teissier inequality.
We have exactly the right number of audience.
Yeah. That's the one. That's right, that's right. Okay, so what I wanted to do in this talk and next talk is to give some proofs of the reverse Khovanskii-Teissier inequality, which appears in different contexts, and I'll go through those three proofs. But first of all, of course, I want to answer like, what is it? So I just stated in the projective setting. So theorem. I'm not gonna be writing this every time, so I'm just gonna write R A T is if I let X be a projective variety, of dimension n over Z, and I let A be C be net Cartier divisors X, then the following inequality, then where any k from 1 to n minus 1, this space is going to be a problem, but that's okay. We have the b to the k, a, and k, rich, k to the k, and c to the n, k. This is going to be bounded below by k factorial is n minus k factorial divided by n factorial, so 1 over binomial coefficient is a to the n b whole. Let's see. Okay, so the product of these two intersection numbers is bounded above, below by 1 over the binomial coefficient times a to the n. So associate these two.
I like.
We can move to the other.
So this is the inequality. So the first thing that one might ask is what's so reverse? And what does it have to do with the Khovanskii-Teissier inequality? So why reverse? So for instance, a consequence of the usual Khovanskii-Teissier inequality is the following. So it's, again, if I have X projective of dimension n over Z, and I have B and C now over X, then one of the consequences is that B to the K times C to the n minus K is bounded below by the n to the K divided by n and C to the n minus K divided. Okay. And so it's reversed in the sense that the usual Khovanskii-Teissier inequality for two net divisors gives us a lower bound on this intersection product number, while this one gives us an upper bound on this number, given a third net divisor. Okay. And another thing one might ask is, at least for me, why is it interesting? Or why do I find it interesting? And for me, and for many of you, I guess, is comes from Lorentz and polynomials. So why? Because it gives us an example. So a criterion with which we can determine whether not a criterion, but just a test to see whether a polynomial comes, Lorentz polynomial comes as the volume polynomial of some divisors in a projective variety. And precisely this gives us an example of the fact that not all Lorentz polynomials are volume polynomials of divisors. Right. And this is an example that I shamelessly stole from one of Jim's papers, which is something like 14x cubed plus 6 squared y plus 24 squared z 12 yz plus 6x z squared 3. And one can prove that this is a Lorentz polynomial.
Remind us what these are behind somebody over.
These are polynomials that satisfy. They are log concave on the upper on the positive orth. That should be one, or that's the general idea. You can have a proper definition, and the proper definition should be something about the log about the signature of each one of the Hessians of the derivatives with degree 2.
For geometers, it is equivalent for this example to the statement that if you write down the Poincare duality algebra, which is defined by that homogeneous form generated by 3 elements, then that satisfies the mixed Hodge Riemann relations. So the example shows that the reverse Khovanskii-Teissier inequality is something that you cannot prove using mixed Hodge Riemann binomial.
Some relaxation of that. Or this much of this. That's. It's polynomials.
Not sure what the section be.
Sorry. You didn't write down the Khovanskii-Teissier inequality, right?
No,
So
it's-
this is just the consequence of it, and that's the reverse because what is being reversed?
The one bounds this coefficient over here. That's the best answer that I got for why it is called like reverse Khovanskii-Teissier. In the sense that Khovanskii-Teissier for a specific case gives you the log, the concavity of some expression like this. This in the case of just 2 divisors, you can get something like this, and then this bounds above bk times c n minus k, while this one bounds below. That one bounds below bk times c n minus k, while this one bounds it above.
I don't think it's a good name.
It's
If
a
you change
name.
the role of ABC, then it's also,
Yeah, I agree. I agree that it's not a great name, but that's
who gave that name?
Not Sergio.
It's not your fault.
I think it's Xiao and Lehman gave that name to it. I mean, the first instance in the literature that I found of it being called reverse, and in this case, they do it with quote marks. They say reverse Khovanskii-Teissier inequality. It's a paper of Xiao and Lehman.
Even they didn't think it was good.
What's up with the A's? Why do you have a RX?
So this one, you can just write it in terms of two. This one, it's a three-term inequality.
Is there a way to think about the A in terms of the?
In terms of what?
Yeah, think of A as something like fixed. A is
Yeah,
like
something
O1
fixed.
and B, C, you vary.
Okay.
Yeah, I don't see how I get from this inequality to these Lorentzian polynomials.
Oh, okay, so this Lorentzian polynomial in this case, you should think of these coefficients as this intersection number.
Oh, I see, okay.
So in this case, let's say that, so that's what I was gonna write. So that inequality written in this language should be something like the normalized coefficient of, let's say that we have k equals 2, no, k equals 1 and n equals 3. So it should say something like the normalized coefficient of this guy times the normalized coefficient of this guy should be greater than or equal. So let me just write it down. So what do I mean by normalized? Then I say that the coefficients are divided by some factorial. So this inequality in this case should be something like 2 factorial 6 times 2 factorial 6. So these are the coefficients of x squared y and x squared should be greater than or equal than 1 over 3 choose 2 times the coefficient with x normalized, so 3 factorial times 14 with x cubed times e to the, so this should be y times z squared. Normalized is 2 times 3. In this case, I'm normalizing them by dividing by the product of factorials of the coefficients of the exponents of the monomial.
That's not numerically true, right?
This is not numerically true. Just what I mean is this
counterexample.
this inequality,
Right.
this is what the inequality would say in that case, and this is the counterexample. This guy is bigger. Another thing that I should say. I am pretty sure that that's. Thanks. So let me move on. I was hoping to have more boards. So you'll have to just commit this to memory and then we'll see.
Maybe write down a tiny version of it and.
I will.
It's also that one.
The inequalities,
That's really beautiful.
Yeah, that's a
Oh,
good
yeah,
place to
it's
save things.
Very cool volunteer.
that's me. That's- I guess I've seen it so many times that I already know, but it's all new.
So I find it helpful to think of the case when A is like O1 on a projective space and B and C lives on some variety that maps to that, yeah. And then it says that it compares the degree of the intersection, degree of the projection of the intersection, push forward of the intersection with the product of the degrees of push forwards. You can intersect and push forward and by the degree, and then there's relation. I think it's related to Bolton's Bezout theorem.
You can think about it as. Actually, that example is the one that proves that this constant over here is optimal. Because you could just write an inequality like this with another inequality here, but with another constant here, but there is an example that realizes this equality. So in which instances does this appear? This inequality first appeared in the Kähler geometry. This was first observed by Xiao and Popovici. Actually, first by Xiao and Popovici, maybe better. And then in that form, it first appears in the paper of Lehman and Xiao. Seen. But then in another paper by Lehman and Xiao, where they're trying to make some correspondences between like Kähler inequalities in Kähler geometry and inequalities in convex geometry, they realize that they can prove a version of this inequality in convex geometry in terms of mixed volumes.
In Kähler geometry, Kähler metric for ABC.
For ABC, they assume that it's their NF, so it's the closure of the cone of Kähler classes, Kähler 1 classes. That's precisely that. Convex geometry is due to Lehman Xiao. And recently there's a one in projective, just in the projective case. But the proof is algebraic. It doesn't use any because in the Kähler case, it depends on this like Calabi-Yau theorem about how you can solve some specific types of differential equations. But in 2023, there appeared a proof by Jiang and Li, which uses Okounkov bodies and doesn't use any of this like differential geometry, differential equations. And I ponder a little bit about how to present these three, and I think chronologically it's best because it like shows how is it like people came to think about this inequality. So let me start with the Kähler one.
Would it be important that you have characteristic zero?
This is in characteristic zero. So you can get this is important also as well because you can prove this inequality not just over a projective variety over C, but also for any projective variety over a field of characteristic zero algebraic.
The third proof is characteristic zero.
Right.
Yeah.
I thought it was characteristic P2.
Characteristic P as well? No.
You know, say Okounkov bodies.
Okounkov bodies.
Yeah, should work right.
Oh, maybe I missed something, but as far as I know, I think it's arbitrary field.
Yeah, it's an algebraically closed field of arbitrary characteristics.
Oh. Arbitrary characteristics.
Yeah, that's the first proof in characteristic.
Yeah, that's right. Okay, so let me talk about it in the context of, since I have not much space for now. So this whole story starts with Jiang and Li, who is studying some so-called holomorphic Morse type inequalities in Kähler geometry. Morse type inequalities. In particular, there is this inequality. In particular, an inequality of the form of the following form. So if I have X compact Kähler manifold, and alpha and beta nets on one classes on this manifold. Next. And they were he was studying an inequality that looks something like this. The volume of alpha minus beta is greater than or equal a n minus n times alpha n minus beta. And what they managed, the volume in this case is for the volume of a 1-1 form, Nef class, say gamma should be something like the supremum over all the representatives, the positive representatives of gamma, the integral over x of t to the n. I'm lying a little bit, actually it should be not the supremum, but also over modifications of x as well. And what Jiang and Li, Bookstone, Alan Peter Nelpud, 07, 930 is a weaker version of this, a restricted. I'll just call this the morphic restricted version of this inequality. And they left it as a conjecture. So this is a conjecture. And okay. So they left this as a conjecture. Yes.
Basic. What is the supremum key? Yeah. What is keying down?
E is so these are classes like homology classes of differential forms.
Okay.
So you're taking the integral over all the supremum over all the elements in that class. And the integral of
What's
the n wedge form of this guy.
gamma is a divisor? Is a class. Oh, that gamma is a class.
Yeah, it's a class.
Okay, I get it. Okay, sorry.
And of
Yeah.
if in Chern homology, so it is a class of differential forms. Each of the representatives of this thing are differential forms.
Is this some kind of bot Chern cohomology?
Yeah,
Because it doesn't depend, it's not independent of the cohomology class. Is what you're saying.
So you can prove that this thing is
What's Chern?
Like, what's the difference between the gamma to the kappa?
The thing is that I'm gonna have a slight difference between alpha to the n. It's gonna be like the integral of, so more like the volume. So I'm gonna make it the following difference. So let's say alpha 1, alpha n times is the integral of
But somehow this is different than the usual cohomology because it wouldn't depend on the usual, cohomology class representative. So somehow this is different somehow.
What's the relationship between alpha to the n and volume of alpha? If they're bound to flip down the other or
I
something?
think if they both net, they're gonna be the same, right? If they're both Kähler classes, so if they're both like ample, should be the same. Just like different notation for different things, for interpreting as a product and interpreting as like a volume.
So can I write like alpha minus beta to the n and just expand the weights?
Yes.
No.
In this case, you shouldn't be able to. No, in this case, you shouldn't be able to because this the there's no interpretation for this unless, should I say this? Maybe I'm not quite sure why there's a difference between writing it as like something to the n or the volume or something.
You're not taking supremum over a singleton set.
Oh, that's right.
And that the volume should be like a volume in the sense of algebraic geometry. You have some line bundle and you compute the dimension of the sections of all powers, and it's like and you look at the leading term and what's the leading coefficient. In algebraic geometry, that quantity is supposed to be that.
Yeah, I guess if these you're thinking about them as like the strength class of some line bundle, then this volume should be the volume of the line.
With that negative.
Yeah, I think so. So we were studying inequalities of this type. And then there is a proof by Bittner of this inequality, but I did the projective setting. So for x projective. And this
Which
is
of the restricted or of the HM?
this one over here, HM. By restricted version of HM, I mean that they add some additional hypotheses to these 1-1 classes. And they also assume that X is projective, not just compacted. But it's not very important what they do, what they actually did. The important thing is that they have this conjecture over here, and this is the conjecture that Xiao and Popovici were trying to prove.
So
But instead of the nef,
yes.
yes, in this case, when I say nef is yeah, the closure of the cube. And what Xiao and Popovici managed to achieve was not exactly this, but something, but like a qualitative version of this inequality. What do I mean by qualitative? I mean that you can think about this inequality as a criterion to determine when the difference of two nef 1-1 classes is big. So when the volume is positive. So you can think about using it when to determine whether this guy is big. And the result that they obtain is something along the lines of, again, X compact Kähler manifold, alpha and beta and F1 classes on X. They say that alpha to the n minus n times alpha to the n minus 1 would be strictly bigger than 0. This implies that the volume of alpha minus beta is positive, i.e. alpha minus beta is big. Okay, and so
What does big mean?
big means that the volume is positive. It's strictly positive.
It's a technical term.
It's a technical.
Doesn't big mean something like the dimension of the powers of the sections of the powers of the line?
Precisely, when you think about.
Coefficient is positive.
Yeah.
This leading coefficient is from this volume.
Is the volume. And when they were proving this, they observed then that they could prove something like our reverse Khovanskii-Teissier, but in the case of k equals 9. So they could, using the same methods, they could prove an inequality like this one, the same methods that they use here. And so that's why they find that interesting. It's because when that this qualitative version of the holomorphic Morse type inequality. So I'm gonna write this HM. This thing implies something like reverse Teissier, Khovanskii-Teissier, where K equals 1. This is again an observation by Xiao.
But in the HM, there are 2 net divisor classes, and with RKT, there are 3 net divisor.
So let me show you how this implies reverse Khovanskii-Teissier for K. So what do we want to prove? We have alpha, beta, gamma. Yes. 1 plus. And then what we want to prove is something, is that inequality, but in the case K equals 1. So this is beta times alpha and it's 1 times alpha gamma and 1 is greater than or equal than 1 over n alpha to the n beta gamma. Okay. And what's the proof? So first assume that all classes are human, or in the language of projective geometry. This is not exactly Kähler. And so in this inequality, we can by scaling, we can assume that beta times that alpha is gamma 1 is equal to beta times gamma minus 1. This is by scaling of beta. And so our inequality becomes something like alpha is gamma minus 1 is greater than or equal than 1 over n alpha to the n, which starts to look a little bit more like this, right? Oh, something, did I do something wrong? Oh, sorry. This is not the one that cancels out, it's this one. Beta times alpha. And so, okay, so we want to prove this. So for the sake of prediction, assume that alpha n minus n times beta alpha minus 1 is strictly bigger than 1. This is the negation of this guy over here. But then so by this qualitative version of the holomorphic Morse type inequality, we have that alpha minus beta is big. But however, since we assumed this over here, we have that alpha minus beta is gamma minus 1 is equal to 0. And this is a contradiction to this guy being big. Why is it a contradiction? There is a criterion for bigness that says that for any Kähler or ample class, there is a multiple of alpha minus beta that is that can be written as the sum of this Kähler class plus an effective class. And so this thing has to be positive. Okay. So this is what they observe.
To go to the net case by.
And yes, and then for the NEF case, since the NEF are the NEF cone is the closure of the Kähler classes, then you just get the inequality by continuity. Questions about this?
Why is it called Morse type?
This is something that I couldn't quite answer. And I think it's because this type of inequality you can obtain by doing some like first first degree approximation of the volume of a function that looks something like this. Of a function of something like this. Minus t beta. And then you let t go between and then this is the so-called Morse function that they are considering on the but I'm not quite sure. So that's my interpretation, is that they get it as like some first degree approximation of something like that. I must say that in these two papers, they don't actually mention this inequality as like something remarkable. It's like just a couple of ideas that they have of something that can be proved. That is implied by the holomorphic Morse type inequality, but it's not actually yet. And then the first proof that I saw appears in this other paper of Xiao, Lehman, where they actually just write it as a theorem, as something that they can. And this is the first instance that I found in the literature of that inequality written in that form. So they already knew that this thing over here had a generalization where you can just like write beta to the k here. But they didn't have a formal statement. So what's the theorem? It's if X is compact and Kähler, of dimension n, and alpha, beta, gamma, F divisors, and F one classes. And now we get beta to the k, alpha to the n minus k, alpha to the k, k is greater than or equal than factorial, alpha to the n, is beta to the k, and now let me prove this in more general. So first, we assume that both the three classes are Kähler, so they're ample. We can do this. Kähler. And then we also assume by multiplying by some constant on both sides, we assume that beta is k is gamma n minus k is equal to 1. So we have some like normalization. And now let's try to write down this thing and then see what we can actually obtain just by looking at it. So we have the beta to the k is alpha to the n minus k times alpha to the k times gamma to the n minus k. So what is this actually? This is the integral over x of beta k times wedged with alpha and that's k times. And the same for this guy. I'm gonna be omitting the x's later. And so these are just like two continuous functions. And so we actually have a usual Cauchy-Schwarz inequality between with the integrals of continuous of positive continuous functions on a complex set. And so this is by Cauchy, just by usual Cauchy-Schwarz. This is less than or equal, bigger than or equal than the integral of beta to the k. This whole thing. The square root of this square. So I'm just using Cauchy-Schwarz, but for the inner product between positive continuous functions on a compact set, that is just the integral of the square root of one times the square root of the other, and that's it.
So to identify NN forms,
Say that again.
yeah, you identify NN.
With functions.
So which method is Kähler? Actually,
I don't think I'm understanding the question.
form is not a function, even
No.
an NN form.
This is yeah. I'm just choosing representatives.
Some global volume form.
Yeah, I'm just using the like. I'm fixing a Kähler structure on X.
Fix one.
Yes. Okay. And now let me revise this like this. This guy over here, I will rewrite as beta to the k, which alpha minus k divided by alpha to the n. So here I'm making the difference between alpha to the n, which is some integral, and just the wedge times alpha to the k, which is k divided by alpha times. And this all divided times. So I'm just multiplying and dividing by some alpha to the n. And now from here, we observe that the integral of this guy is this end product. And so what we need to bound is this guy over here.
And now you're back in the land and end forms.
And I'm in the land of n. Yes, that's why I'm making an effort to distinguish between the ones that are just these products and ones that are just. Since I said Kähler, I've just been talking about classes of forms. Okay,
Sorry, sometimes the exponent you write this wedge, sometimes you don't.
because I'm making the difference between this guy, which is the integral of alpha, which with itself and times.
And that, let's say, beta to the k in the middle, that's which one?
This one, for something that's less than n, it's always a wedge.
Okay.
Maybe I'll write that. These are wedges, these are not wedges. I know it gets confusing.
You want to prove something point by point.
So what I'm gonna try is to prove something point by point. But what I'm gonna do first is notice that we have a choice of a representative for alpha. So for this, all these equations, we have a choice of a representative. So we can choose our representative. And we're gonna choose the following. And this is where like really big guns, really big theorems are being used to, I don't know if it's a big theorem, but it's something that I don't know the proof of. Something is used to prove this inequality is that by the Xiao theorem. There exists here a function psi, a unique psi, that is a solution to the following equation: alpha plus I times del bar psi all wedged to the n is equal to alpha to the n, no wedge. So this is the integral of alpha wedge n times beta to the k wedge gamma to the n. Okay, so let me maybe say a little bit about this. So what does the Calabi-Yau theorem say? This type of equation is a differential equation, which is called, it's of a type that is called a Monge ampere equation. And the Calabi-Yau theorem. The Calabi-Yau theorem tells me that this type of equation has a unique, there exists a unique solution for this function psi, or any form that I choose here, or any Kähler forms that I choose here. And of course, these two guys can butt train commodity because it's just alpha plus I times some delta bar of psi. This is gonna be in the same class. So alpha and this guy. Maybe I should write this in there. Alpha and alpha sub psi, this guy over here, are in the same class, are the same.
Would you think be positive?
Yes, should still be positive, right? I'm not sure if that's something that the Calabi-Yau theorem guarantees. I think that in this point, I'm a little bit lost. I'm just regurgitating what I found, what I read.
So, question.
Yes.
We have alpha beta, so we have alpha beta gamma fixed Kähler.
Mhm.
And then we get that's
Yes, if,
okay.
this guy in reality is not that incredibly important, but the important thing is that there is a solution to this equation. And so in that, in our inequality, we can just like change all the alphas over here for alpha psi. And more importantly, then what we need to prove or not what we need to prove, but something sufficient should be something like beta to the k, which gamma to the n minus k. Oh, sorry, not gamma, alpha psi to the n minus k times alpha psi to the k, which gamma to the n minus k. This divided by alpha psi n divided by beta to the k, which gamma to the n minus k. If we prove that this is bigger than or equal than 8 factorial n minus k factorial divided by n factorial, then we have the inequality. One by one. If we prove that this is satisfied, pointless. Now we're run out of space again. Maybe I'll continue here. There you go.
Why is it not?
If this is satisfied, then here, this alpha to one of these alpha to the n's, we can replace all of these with alpha psi because it's their classes. These equalities are satisfied. And if we change one of these for this thing over here, then we're gonna get this thing over here divided by alpha to the n. So if we prove that this is greater than or equal than this, then we can take it out of this whole thing. And then we're gonna get alpha to the n squared divided by alpha to the n. And then we get this inequality. Maybe.
But why were we allowed to change the psi?
Because this integrals don't, this products are not depending on the class. So we, in fact, we could, I could have just like changed it from the beginning. This shouldn't depend on the class.
And only on the class.
Phrasing, I guess. If I switch a couple of two from the, yes. They depend on the only.
That's functions on X.
Which ones?
What does pointwise mean?
Pointwise means as functions in it, because like this, these are functions in X.
The identification.
Yes.
There is no identification for n form divided by n form.
Oh,
The normal coefficient is optimal. No?
It is something. Maybe I'll work. Let me just like finish the proof by proving that this inequality holds. So for any point P next, we can choose coordinates so that alpha is I just the ZZs. So the beta, I can write something with some coefficients uj. This is locally, of course.
Here you use this alpha psi is positive.
Yes. And gamma to the n minus k I'm gonna write as I to the n minus k times I for some coordinates, okay? Some functions, coefficients. Gamma. So I j g z I, which this is the wedge of the ones that are in this subset. But this is just notation. And with these, with this choice of coordinates, that inequality over there, that expression over there, becomes only something like n minus k factorial times the sum over all the subsets that have size k, mu j, divided by n factorial times k factorial, the ones that's up to k, 1 minus k, gamma I, okay, with the repeated ones. Divided by 2 of the ones in k of O j sum k component j. And if we just rewrite this with a little bit of care, this is just k factorial divided by 1 factorial times this guy times this guy divided by this. But notice that this sum over here is just the sum of terms that appear in the product of this two sums. And this one has more sums than this one, and all of these elements have to be, since we assume that they are Kähler classes, all of these have to be mu j and gamma j, ij have to be positive. So if we evaluate them at a point, there are more terms down here than there are here. There are more terms upstairs than there are downstairs. So this is, so the product of this guy with this guy divided by this guy has to be greater than or equal to 1. And so this is bigger than this.
In this description, which quantities are positive? The mu's and
The mu's and the gammas. Mu's and gammas are positive.
That's all gamma on the I.
Gammas II have to be positive, that's right.
To be something positive definite.
Yes. Yes. Yes, I agree. So since these are Kähler classes, then mu j has to be positive and gamma I. That's true. And then this finishes. So the interesting thing about this proof is that it requires, at least with this techniques, we need to use a Calabi-Yau to solve this representative inequality, and then we can actually prove it.
What's the relation between this Calabi-Yau and the one I am used to with some relation between Kähler and figure that
I am not sure. So how I've the actual, like the only versions of the Calabi-Yau theorem that I found were something like if I have omega Kähler class. And EV a volume form. If omega to the n is the same as the integral of this volume form over here, then there exists a modification of omega, let's call it tilde, so that this is true. That is the version of the Calabi-Yau that I found. I don't know how the other one relates to anything else. And then I think maybe I'll stop here and then next time I'll show the convex geometry counterpart and the Okounkov body. Sorry if it was very confusing. There are many like moving parts and this is not I think this is not something that we all are like very familiarized with, but I just wanted to show the